In this video, we're going to explore the concepts of periodic properties and periodic trends. When the periodic table was first arranged, it was done so in order of increasing atomic number. Periodic tables were actually set up before electron configurations of elements were known. People like Dmitri Mendeleev and Lothar Meyer were able to do so because the properties of elements are periodic. In other words, these properties repeat themselves every so often. For instance, lithium is a very soft, silvery grayish metal which reacts violently with water. 8 elements later we come to sodium, a silvery grayish metal which reacts violently with water. 8 elements later we come to potassium, another soft, silvery grayish metal which reacts violently with water. Mendeleev and Meyer saw these sorts of periodic properties everywhere they looked, and were able to set up a periodic table based on that. And so what we're going to look at in this video is how we can use the table in order to predict certain trends of atoms. These periodic trends are so powerful that Mendeleev was able to predict the properties of germanium before germanium was even discovered. In 1871, he was able to predict things like the atomic mass, density, specific heat, and all sorts of properties, even though the element itself was not discovered for 15 years. Many of the properties that we're going to talk about in this video are a result of something called effective nuclear charge. The effective nuclear charge is the net charge which is experienced by an electron in a multi-electron atom, which results from a balance of the attractive forces of the nucleus and the repulsive forces of other electrons. The effective nuclear charge, often called Z effective, increases across a period because of incomplete screening by other electrons. In other words, the charge from the nucleus that an electron, quote, feels is reduced due to the repulsive effects of other electrons that may be closer to the nucleus. And so, for instance, the effective nuclear charge of a 4s electron is less than the effective nuclear charge felt by a 3p electron, because the 4s electron is further away. It feels the nucleus less than a 3p electron does. In order to calculate the effective nuclear charge, we will simply take the atomic number and subtract the number of inner electrons. And so if we're looking at the charge felt by a 2s electron in lithium, our atomic number of lithium is 3. We have 2 inner electrons. Our Z effective is equal to 1. For beryllium, atomic number is 4 minus our 2 inner electrons. Our Z effective is 2. For a boron atom, atomic number is 5 minus our 2 inner electrons, for an effective nuclear charge of 3. And this just shows us some more examples. So once again, Z effective is equal to our atomic number Z minus the number of core electrons, which are the electrons doing the screening. They're the electrons that shield those outer electrons from feeling the pull of the nucleus. And so the effective nuclear charge for sodium, 11 electrons total, minus 10 core electrons for an effective nuclear charge of 1. Magnesium, 12 electrons minus the 10 core electrons, for an effective nuclear charge of 2. Let's look at this in another way, which might be a little bit easier to visualize. Let's say we're moving across the periodic table from left to right, and let's look at atoms in the third period as we were before. And so we'll take a look at sodium, magnesium, and aluminum. In the case of sodium, we have our 11 protons in the nucleus. And then for the sake of simplicity, we'll just draw all the core electrons together. So we have 10 core electrons for sodium. And then our outer electrons, we've got 1 electron in our outer shell. And so in the case of sodium, we have our 11 pluses and the attraction of our 11 minuses. In the case of magnesium, we're now going to have our 12 protons. We also have 10 core electrons. And now we have 2 electrons in our outer shell. And so with magnesium, we've got 12 pluses pulling on 12 minuses. And then for aluminum, we've got our 13 protons. We've got those same 10 electrons in the core. And we now have 3 electrons in our outer shell. And so 13 pluses pulling on 13 minuses. If we think of this from purely a forces of attraction between charged particles point of view, we see that in the case of sodium, we have 11 positive charges pulling on 11 negative charges. With magnesium, we have 12 positive charges pulling on 12 negative charges, and aluminum 13 positives pulling on 13 negatives. And so as we move from left to right, we have more charges, and so we have a greater force of attraction, leading to a greater effective nuclear charge. In other words, there's simply more of a pull between the nucleus and those outer electrons due to the increasing number of charges. This point of view will help us to visualize some of the periodic trends that we look at shortly. The first trend that we're going to look at is the size of an atom, or the atomic radius. First, let's think about what happens as we move from side to side in the periodic table. As we go from left to right, our effective nuclear charge increases. And so that means that the pull on those outer electrons increases. And so as we go right to left, our size is actually going to decrease. Again, because of a larger effective nuclear charge. The outer electrons literally feel more pull as we move left to right, and so they will be pulled closer to the nucleus. And so our size increases as we move from right to left in a given period. As we move down a group, however, we go to further and further out Bohr shells. And so the effective nuclear charge is no longer the main player in the size of elements. Now, it's simply the fact that we're moving to further and further out Bohr shells. If we're talking about period 1 with just a hydrogen atom, we have our nucleus and just one Bohr shell. Period 2, lithium, beryllium, boron, and so on, we have 2 Bohr shells, and so on down the line. And so our outer electrons are moving into further and further out Bohr shells, which will increase the size of the atom. And so we can see that in this diagram. If we're looking along our second period, we see that our size generally increases as we move from left to right. In our third period, again, we see the same thing, and we see that same general trend everywhere in the table. And then as we move down any given group, we also get larger. This leads us to saying that the elements in the very lower left-hand side of the periodic table are the largest, and helium, being in the very upper right of the periodic table, is the smallest. And so to recap for atomic size, the size of an element goes up as we move down a group because electrons are added further and further from the nucleus, and so there is less attraction felt. And the size goes down as we move across a period from left to right because the effective nuclear charge will increase. The next trend we're going to look at is something known as ionization energy. The ionization energy of an atom is the amount of energy required to remove an electron from the ground state of a gaseous atom. And so IE1 is the energy needed to remove the first electron. And so in this case here, we're looking at a potassium atom. We supply it with energy to remove one electron and form a potassium plus one ion. And then the energy for that would be 419 kilojoules per mole. IE2, the second ionization energy, would be the energy needed to remove the second electron from that plus one ion. And so here we have potassium ion plus that ionization energy 2, which would give us a potassium 2 plus ion. And we see that takes much more energy. Now just think about what we know from what we've looked at earlier in the course. We know that naturally potassium wants to form a plus one ion. At that point, it will be in a noble gas configuration, which is a stable configuration. It really does not want to lose another electron, which is why in order to form a plus 2, it would take a lot more energy. We'll be returning to that idea later on. The general periodic trend for ionization energy is that as we move from left to right, our ionization energy increases. It takes more and more energy to remove an electron. And as we move up the table in a particular group, the ionization energy also increases. Now let's take a look at why. And so if we look, for instance, across period 3 again, if we look at sodium, sodium begins with its 11 protons and 11 electrons. And so it takes a certain amount of pull to remove one of those electrons to form a sodium ion. With magnesium, we've got our 12 protons and our 12 electrons. And so we have a greater effective nuclear charge. With 12 pluses and 12 minuses, those electrons are held in more tightly than they are with sodium. So it's going to take more energy in order to remove it. Now let's think about what happens as we're moving up a group. If we're going, for instance, from a sodium atom to a lithium atom, sodium is going to have electrons, its outer electrons, out in the third Bohr shell. Lithium, on the other hand, is going to have its outer electrons only in the second Bohr shell. And so in a lithium atom, those outer electrons are a lot closer to the nucleus, and there are fewer electrons in the core, which would shield that effective nuclear charge. And so since that outer electron in lithium feels more pull than the outer electron in sodium, it's going to take more energy to remove the outer electron of lithium. The other way to think about it is simply that as we move down the periodic table, the outer electrons become further and further away from the nucleus. They feel the charge of the nucleus less, and thus they are easier to remove. And so a francium atom will have the lowest ionization energy of anything in the periodic table. In fact, it is so low that francium basically does not exist in its atomic state. The ionization energy is so low that if you had a neutral francium atom, that electron hardly takes any energy at all in order to remove. So let's look at the energy associated with removing one electron. So the general trend is that ionization energy 1 is going to be less than ionization energy 2, less than ionization energy 3, less than 4, and so on. That's because as we remove electrons, we start to have a greater attraction for the nucleus, and it becomes harder to remove subsequent electrons. We also notice that in the case of lithium, the jump from ionization energy 1 to ionization energy 2 is much greater than the jump from 1 to 2 for beryllium. The reason for that is that once lithium has one electron removed, it achieves a noble gas configuration, which is very, very stable. In the case of beryllium, once we remove one, we can still remove another electron before it attains that electron configuration of a noble gas. And thus we get a big jump between 2 and 3 for beryllium. We can see that same sort of trend reflected in some of these bar graphs. In the case of sodium, we see a big jump as we move from the first to the second ionization energy, because the removal of one electron from sodium gives us the configuration of a noble gas. Very stable, and thus it will be very hard to remove one of those electrons after that. Magnesium. Fairly easy in relative terms to remove the first and the second electrons, but then we achieve the configuration of a noble gas, and so it will take a lot more energy in order to remove the third. And the same with aluminum. We can remove 1, 2, and 3 fairly easily, but at that point we've achieved the configuration of a noble gas, and so it would take a lot more energy to remove the fourth. We can use that sort of information to predict what group an element would be in. We see here that we have unknown element X, in which the first 4 electrons are fairly easy to remove, very hard to remove the fifth. That tells us that element X is going to be in group 4, the carbon group. We don't necessarily know which one from this data, but we can pretty safely say that it is in group 4. Likewise, element Y would be somewhere in group 6, oxygen, sulfur, selenium, and so on, because the first 6 are relatively easy to remove, and we get a big jump after that. And so we see similar trends here when we look at the first 7 ionization energies of several elements. We can see that in the case of sodium, we get a big jump after the removal of 1 electron. After magnesium, our big jump after the removal of 2. Aluminum, our jump after 3. Silicon after 4. Phosphorus after 5. Sulfur after 6. And even though we don't see it here, there is a big jump after removing the 7th for chlorine. And so again, that gives us a way to predict the group number by analyzing these trends in ionization energy. The last periodic trend that we're going to look at is electron affinity. So if ionization energy is the energy that it takes in order to remove an electron, electron affinity is just the opposite. It's the energy change for the process of adding an electron to a neutral atom in order to form a negative ion. And in the case of chlorine, so chlorine plus 1 electron to form chloride, we see that the energy is negative 349 kilojoules. And so remember, negative energy means that it's an exothermic process. So it actually releases energy. And recall that the sign for energy, the negative sign here, means that this would be a thermodynamically favorable process. The general trend for electron affinities are that they increase as we move left to right and up in the periodic table. And we can see that general trend here when we look at the halogens. It is important to note that with electron affinity, there are several exceptions to the rule for various reasons. And so whereas we do see a general upward trend here, we do see a break in that pattern when it comes to fluorine. There are some elements, like the noble gases, that do not have electron affinity values, simply because they have no affinity for electrons. Noble gases are already stable with their electron configurations. They really do not want to have another electron added. When we compare the two, we see that ionization energy measures the ease of losing an electron, and that's always an endothermic process. It will always take energy to remove an electron. Electron affinity measures the ease of gaining an electron. That is often an exothermic process. It often releases energy, but not always. And so to recap our periodic trends, the atomic radius, as we move down a group, will increase. As we move across a period from left to right, atomic radius decreases. Ionization energy, we move down a group, will decrease. Left to right across a period will increase. And electron affinity, as we move down a group, becomes less exothermic. And left to right across a period becomes more exothermic. And so in this video, we've taken a look at periodic trends and what structures of the electrons in the atom cause the trends to behave the way that they do. I hope this has been helpful. If you need some additional help, be sure to come see me, go see a tutor, or attend a past session.